Hi everyone, and this is the presentation in 2022 NOMS. I'm Chia-Cheng, the presenter of our research. I will be talking about our work entitled Graph Neural Networks based root cause analysis using multivariate time series KPIs for wireless networks. This research primarily studies root cause analysis and focuses on what the impact is if we can exploit the machine learning and KPI data. And this work is based on the work with Gaia T Neutron at Ericsson last year when I was doing internship with Ericsson. Okay. And in this presentation, I will introduce our motivation and challenges, and then I will move on to a short summary of our achievements and our proposed method to address node failures that would happen in wireless networks. And finally, I will show you some of our experimental results in the final section. Okay, and the major motivation that drives us is the ever-increasing scale of networks in our world as advanced wireless technologies have been developed and new devices are growing rapidly over the past decade. This development will inevitably increase the cost and complexity of network operations and management in the near future. In response to this, the design of the new root cause analysis method has to be able to adapt to a large size of network, increase fault tolerance, as well as reduce human intervention. Moreover, we also struggled for information which does not show up in the dataset or missing data caused by aggregation. And as we moved forward, we realized that not only the design of machine learning model is difficult, but acquisition of useful data set and prediction of potential relationship among nodes are also very challenging because the data set we obtained might not as useful as we thought, and the information is usually incomplete. So how to extract useful knowledge and infer hidden information are also important parts of this research. All right, so um, a short summary here is we want to develop a graph neural network based method to identify root causes which can lead us to an important impact, increase the level of diagnostic automation and get us a little bit closer to self-healing and self-learning networks that require minimum human intervention. Okay. To predict potential root causes, we propose a GNN-based root cause analysis model, leverage KPI data as node features. And no features are first extracted from time series dataset and graph structure learning model, then applied to node features to infer hidden relationship among nodes. So here, what I mean hidden relationship is the graph structure. For example, which nodes are the neighboring nodes and which node are non-neighboring nodes. And this information is essential for a GNN model to learn, but is usually missing in dataset, which increases the difficulty of performing root cause analysis. And once the graph structure is predict the structure and feature as input data are fed into a GNN model. And the GNN model will learn how to map nodes onto the lower dimensional space by fine-tuning neural parameters. And by doing this, the model separates the potential root cause and the other victim nodes. And then based on the root cause and the victims, a chain of failures can be discovered. So in this research, our contributions are first, we use KPIs and graph structure learning model to predict the graph structure to address the information missing issue. And then we apply a GNN model to the predicted graph to identify root causes. And later, I will show you the root cause analysis result of using a graph convolutional network and a graph attention network. And we found that better accuracy can be achieved if more and more nodes can be included in experiment. Okay. And in this research, we simulate a scenario where a node or a base station fails, and this would impact the network. Tracking this event to find the root cause of the change is the goal of our study. In this simulation, we assume that a combination of 4G LTE and 5G NR ranges are randomly distributed over an area. The size of this area is assumed to 3 kilometers by 3 kilometers. And GNOBs and eNOBs are considered as nodes, each of which is associated with multivariate time series KPI data as features reflecting its performance. And the KPIs pertaining to a node at a given time period can represent a feature which an AI-enabled agent can learn from to predict labels that signifies which nodes are potential root causes using deep learning model. And the time series KPI data of nodes are collected from the 5G network and utilized as input to infer the graph structure by graph structure learning model. And the predicted graph is used to train a GNN-based root cause analysis model. And we formulate the root cause analysis problem as a classification problem. Our goal is to minimize the loss between the predicted root cause nodes and the observed root cause nodes. Okay, and in the time series data, a node feature during a time period is represented by a vector of KPIs observed at that time period in 5G wireless environment. And the KPIs include reference signal receive power, RSRP, reference signal receive quality, RSRQ, and received signal strength indicator, RSSI, and signal to interference noise, SINR, and throughput. So they are the KPI data we use. And as mentioned, because the missing information of dependencies in the data, the node features are used to infer a relationship dependencies among nodes in the same geographical area. And the graph structure learning model proposed by the following paper is applied to a given set of nodes with features to learn a weighted adjacent metric which predicts relationship dependencies among the nodes in close proximity to each other. And the model takes node features as input where theta 1 and theta 2 are linear layers, and alpha here is a control variable. And the generated matrix A representing the connection likelihood among nodes. And from this weight, each node only select its top k highest connection or top k highest weight as its neighboring node to predict relationship dependencies. And these predicted dependencies or edges are used to build an input graph for data. for data classification in the next step. And the node features combined with the edge information is the graph structured input data upon which the proposed GNN model explores different possible causes and analyze them if some part of a network goes wrong. Okay. And before I dive into the GNN model, I would like to spend some time to help you understand some of the differences between GNN and the other deep learning models. As you might already know, deep learning highly relies on features of input data to learn meaningful embeddings during the entire training process. But most new deep learning models are designed for either images, two-dimensional data, or sequence data, one-dimensional data like audio. If we want our model to learn, we first have to, generate something that is meaningful to them. And obviously, CNN is not a good fit to network problems because it's a specialized approach that is designed to address data with a regular Euclidean structure like two-dimensional data images. So it is hard to encode network graph into like a two-dimensional grid structure. But in comparison, GNN is more generalized and can handle non-Euclidean data, such as social networks or telecom networks. Okay, and based on that, we choose GNN as our model to process the graph data and learn how to um, predict a root cause by mapping nodes onto lower dimensional space that can maximally separate the nodes. And for each iteration, a feature of each node is propagated to its neighboring node to generate embeddings for all the nodes in the graph. And the features from neighboring nodes of a node are aggregate and feed into a transformer neural networks that transform input features into an embedding by tunable neural weight within the neural network's hidden layers. Then the new embeddings generated in the current iteration will be the features in the next iteration. And the aggregation and the propagation continue until all nodes get updated by their new embeddings. Okay. And throughout the entire training process, right, GNNs fine-tune the weight that output optimal embeddings that can be mapped onto latent space for separating the potential root causes and the other victim nodes. Okay. And last but not least, I will show you our experimental result here. We applied GNN models in this research, and one is graph convolutional network, GCN, and the other is graph attentional network. But due to time limitation, here I'm going to show you GCN only. And we have three experimental sites. They are 7, 8, and 9 nodes. As you can see in the figures, red lines indicate loss, and the blue line shows the performance of GCN. And in our experiment, we found that learning performance of GCN model or GNN models can be improved if the number of nodes is increased. And the possible reason for this is because the simulated data set do not provide satisfactory information for the graph structure learning model to infer an appropriate graph structure. And because the predicted graph structure is not accurate enough and the number of features is not great enough, the performance of GNN models would then be influenced. So a sufficient number or more number of node participate can provide enough feature for graph structure learning model to predict a graph structure that can accurately describe relationship dependency over a graph. So later, the GNN models can rely on some accurate graph structures and perform aggregation and propagation using these features, as well as learn from more features during training. So that's the reason why we can have more accurate result if we can, include more participating node. Okay, and this is all for my presentation, and thank you for your attention.